Welcome. In this lesson, we are going to tackle false positive constraints. The subtitle is How Not to Be the Boy Who Cried Wolf, because false positives are basically false alarms. Let's discuss this in more detail. Binary classification is the machine learning problem of classifying into two classes. One class is known as positive and the other as negative. Binary classification is super common. To give you some examples, spam versus ham classification, malware versus benign, phishing versus legitimate website. Logically, there are two ways to misclassify, to make mistakes. You can classify a positive as negative, and this is known as a false negative, or you could classify a negative as a positive, and this is known as a false positive. To illustrate this, let's say that we are doing a malware versus benign classification. Malware is our positive, benign is our negative. So if I see a malware and I let it slip because I classify it as benign, that's a false negative. On the other hand, classifying a benign as malware would be a false positive. Similarly, if I am classifying spam versus ham, spam is positive, ham is negative, then if I miss a spam, that's a false negative. But if I incorrectly take your email and mark it as spam, that's a false positive. False positives are effectively false alarms. They cause time to be wasted for employees and IT people who have to check what the alarm is about. And in fact, a large false positive rate can be even worse and more costly than being hit by malware. Hard to believe, but that is reality. Often consumers of cybersecurity products want a limit on the number of false positives. For instance, they might want no more than 0.1% false positive rate. You and I don't want any of our important emails to be classified as spam. If some email gets classified as spam once in a while, it's not a huge deal, but if it happens repeatedly, then you'll get annoyed and you'll switch service. So given that this is quite important to limit the number of false positives, how do you actually do it? How do you make your classifier meet such a constraint of 0.1% false positive rate? A technique for doing so is called thresholding. To understand thresholding, imagine the following illustration. Suppose you have a classifier that, given some input, outputs a probability pair. The pair consists of the probability of being negative and probability of being positive. For instance, it could be XGBoost. Usually, to decide what the file is according to the classifier, to give a prediction for a label, we pick the higher probability. If it says 85% likely to be a negative, 15% likely to be positive, we say, well, it's more likely to be negative, and therefore we should assign it a negative label as a prediction. In other words, ordinarily, our algorithm for assigning a label is look for the probability of the first class being bigger than 0.5, then you'll assign it to that class. Otherwise, you will assign it to the other class. In thresholding, on the other hand, you will bias the predictions using some threshold which you will compute, thus making it more likely to predict one class over the other. So let's say that I picked my threshold to be 0.7, and let's say that my classifier looked at an example and it gave the probability pair 60% and 40%. 60% likely to be a negative. Before we would say, well, it's more likely to be negative, so it is predicted to be a negative. Now, since we chose a threshold to be 0.7, we ask, does the probability of being negative exceed the threshold? If yes, okay, then it's a negative prediction. But if not, then it's going to be a positive. So you see that overall, we are now going to increase the number of positives that we're going to have in our prediction, thus reducing the odds of making the incorrect prediction of a negative. So you can think of this as sort of just biasing towards one of the classes. And what we can do is pick the correct threshold so that we can have our false positive rate meet our expectations. Let's start by loading some data consisting of malware and benign features and specify our goal false positive rate. We define a function to calculate the false positive rate. So it's going to calculate the total number of negatives, the number of false positives, and then it's going to use a formula to get the false positive rate. And similarly, we'll define a function to calculate our true positive rate. The true positive rate is the proportion of positives that we actually catch. You can also think of it as coverage, or how many malware or spam you're able to catch out of the total that's coming your way. Now I'm also going to define a function to to threshold a vector. So it's just going to take some threshold, which I will feed in, and a vector, which will consist of a bunch of probabilities, and these probabilities will be thresholded using the formula which you see. Next, I'm going to train some simple classifier, in this case logistic regression, on my data. And then I'm going to use logistic regression to get a prediction probability, so a pair like we have discussed so far. Next, I want to find a threshold which will guarantee my false positive rate. And the way I'm going to do it is try out a range of possible thresholds. So I'm going to try out every threshold between 0 and 1 in increments of 0.01. And for each of those thresholds, I'm going to use my thresholding algorithm to obtain predictions, and then I'm going to see what is the false positive rate and what's the true positive rate in those instances. If the false positive rate satisfies my constraint, then this threshold will be a candidate, and at the end I'm going to pick the best threshold based on the true positive rate. So here are the probability pairs, and now you can see the loop over the threshold. First, the false positive rate is extremely high, and so is the coverage. As we start dropping the threshold, we are able to reduce the false positive rate, but we are also sacrificing some of our true positive rate, our coverage. And you can see eventually we found a threshold that met our false positive rate, and it has a certain coverage. So this is how you select a threshold to guarantee that during training, at the very least, you will meet a false positive constraint. Next up, we're going to cover malware dynamic analysis, which is about how to analyze malware by actually running it. See you at the next lesson.